This problem is about a counterflow heat exchanger, and this is example 7.6 from your textbook. So we're going to go through it in detail, but I will be certainly skipping some parts, which you can refer to in the textbook if you need to, or get back to me if you have any questions. And before I start, I'll just give you a hint that we will be using the ideal gas tables here. Okay. So it's as we read the question, we'll understand why do we need to make use of ideal gas tables. Okay, so we have compressed air, which enters a counterflow heat exchanger operating at steady state, and it's entering at this condition. Okay, so this is the condition at which the compressed air is entering, and it's exiting at almost the same pressure, but at a much higher temperature. Okay, 860 Kelvin. Now, hot combustion gases enter as a separate steam as at 1020 Kelvin, certainly a much higher temperature, and exits at 1 bar. Okay, so exits at more or less similar pressures. There is some pressure drop because of friction losses within the pipe. Uh, we don't know what's the temperature, but we know the exit pressure is 1 bar. Now, each stream has a mass flow rate of 90 kilogram per second, so that's good. We know the mass flow rate already. The heat transfer between the outer surface of the heat exchanger and the surroundings can be ignored. So effectively, there's no heat loss from the heat exchanger to the surroundings, right? So the Q is 0, but there is, of course, heat transfer happening between these two streams, which is why we had the heat exchanger, okay? Now, the effects of motion and gravity are negligible as always. Assuming the combustion gas stream has properties of air, this is an assumption, probably a reasonable assumption. And using the ideal gas models for both streams, we need to determine for the heat exchanger a couple of things. Okay. First, we need to determine the exit temperature of combustion gases. So we want T4 here. Okay, that's the first part. Second, we want to determine what is the net change in the flow exergy rate from inlet to exit of each stream. All right. So when you talk about flow exergy rate, we're talking about EF, right? So we want to determine what is EF1 minus EF2 or EF2 minus EF1. What is the difference of EF, right? Between inlet and outlet. So here, probably here you can talk about EF2 minus EF1 because this is coming out at a high temperature. And for the other case, you could be looking at EF3 minus EF4. You can do either way you like. Okay. All that we're looking here for is the difference. We're looking for the net change. How much change happened, right? And lastly, we're looking at how much is the exergy destruction. Okay. So again, these are three different things that we're looking at. And as we had explained in the last problem, the part A and B are sort of giving you the hint towards going towards part C, right? So you need to know the things in part A and B before you go and calculate how much the exergy that's getting destroyed. So these are the conditions given for T naught and P naught, right? And so let's just go ahead and start solving it. So this again is a very interesting problem, a very practical problem that you will see in all heat exchangers. Okay, and here let us see how much exergy is destroyed, and let's see what we can do about it, right? Let's talk about it as we go through the solution. Okay, so this is the exergy rate balance that we will have to use. Okay, and before we even go ahead, one thing is pretty straightforward. There's no heat loss to the surroundings, so the first part is 0. Okay, what about work done in a heat exchanger? 0, non-zero? Yes, of course 0, right? So we are just dealing with this change in flow exergies and exergy destruction, which is why sort of that is what has been asked, right? So we had to calculate part A, part B, and then go ahead to part C. And the reason we need to calculate part A before we go to part B is because we don't have the state defined for the combustion gases, right? We don't know T4, so we need to first determine T4. All right, so let's go ahead and let's start solving this. We have the stream here. Okay, mass flow rate is given, temperatures are given. Luckily, mass flow rate is same, right? Now the question is, how do we go about, determining the exit temperature? How do we proceed here? Yes, Abdullah.
Ideal gas equation.
Yes, you can make use of ideal gas equation, but the problem is that we don't have enough information at the exit state P4 to determine the temperature. So uh, this is the ideal gas equation. We only have the pressure. We have no idea about the specific volumes. So we really cannot determine the temperature. Yes, Hassan.
Maybe we can use the heat exchange between both streams.
Mm-hmm. Yes. So you mean we apply some sort of energy balance?
The Q lost from one stream goes to the other.
Yes.
We have the information for from 1 to 2.
Mm-hmm.
Uh, we can
Yes,
find T2, T4. If we
exactly.
find the heat for 1 to from 1 to 2, we can use it the same heat from 3 to 4 and find the enthalpy. I think
Yes,
from the enthalpy we find the heat from the table
perfect.
at the temperature.
Temperature. Yes, exactly. Excellent job, Hassan. That's exactly what we need to do. Okay, and here again we have to make use of ideal gas tables, and we are assuming the specific heats to be variable, right? We are not assuming constant specific heats because nothing is given in the question, right? So by definition, we assume that the specific heats are variable, and therefore we go to the table and make use of enthalpies instead of just relying on temperatures and using Cp delta T. So we don't use Cp delta T's here. And as Hassan mentioned, it's simply about energy balance, right? You need to apply energy balance to this to the heat exchanger. Now the heat exchanger as a steady state steady flow system has the property that what the energy that's coming in is equal to the energy that's going out, right? So now I could there are several ways how I can go about solving this. I can also say that the heat gained by this air by the cold stream from 1 to 2 is equal to the heat lost by the hot stream, right, from the energy perspective. Or I could just follow this formula and write the different things that are coming in, different things that are going out, and move ahead with it. Either way is very good. Okay, so let's just go with the method Hassan mentioned. So the heat uh, so let's write the heat gained by the cold fluid, right? So when we talk about the heat gained by the cold fluid, we are just talking about m dot times H2 minus H1, right? This is what is gained by the cold fluid. And on the other hand, this is equal to the energy lost by the hot fluid. So this should be equal to m dot H3 minus H4. Okay. Here, I mean, the mass flow rate is the same, so you can cancel it out. And then we can just uh, send H3 to the other side so that we have H4 is equal to uh, H3 plus H1 minus H2 or H4 in terms of the other three enthalpies, right? So when you do that, this is what you get, okay? And now all we need is to get the three enthalpies right here, okay? Now we have the temperatures provided, and since we are treating all these as ideal gases, we know that enthalpy depends only on temperature. So you go to table 822 at temperature of 610, you get the enthalpy as the 617.53. Same way for T at T2 and T3, we get these values of enthalpies. We have everything that we need here. We can plug that into this equation and we get the enthalpy at state 4. Now, this is again, this is the enthalpy at state 4, but what we actually need is the temperature. And again, since we know that for an ideal gas, enthalpy is only a function of temperature, so you can go to the table, do some interpolation, and get the temperature at T4. So the exit temperature comes out to be 778 Kelvin about, or 505 degrees Celsius. So this is simply how we need to apply. This is how simply we calculate the exit temperature, right? So it's simply about applying energy balance. So this is a simple way of going ahead and solving for part A. Any questions here?
Clear.
Okay. All right. So in the slides, I did using a general way. So on the blackboard, you will see that we start with energy in as energy out, and then I show you the different forms of energy and cancel it out. For those who are not very comfortable going straight away to applying the energy uh, balances, in the sense that if you're not comfortable going straight away and writing energy gained by one stream as equal to the energy lost by the other, you could use that as well, or you could see what we did. Both of them are going to give you exactly the same answer, right? Okay, so that's done. Now let's look at the second part. We already know the temperature at state 4 now. So basically all the states are defined. Here we just need to get the net change in flow exergy. Okay, so again coming to this part, we're looking at net change in flow exergy for both for the two streams that we have here. Okay, so let's start with the air stream. So net change in specific flow exergy for the air stream would simply be equal to this term right here, because we don't have any uh, appreciable changes in kinetic and potential energy, right? We said those are considered negligible. So all that we need here is enthalpies, okay? Enthalpies and entropy differences. Enthalpy is very straightforward. We already have the enthalpies. We can plug them in. Now the entropy difference that you need to get here, again, since we are treating this as ideal gas with variable specific heat, so you need to make use of S2 naught minus S1 naught minus RL and P2 by P1 formula, right? So this is the formula when you have variable specific heats. Again, this formula is mentioned in the formula sheet. You just have to be careful to pick this up and not the other one. Okay, so this is how you go ahead and solve it. Again, when we are looking at the different terms, mass flow rate has been provided in the question. H2 and H1 we already know because we got them for part A, and these are just functions of temperature. S2 naught and S1 naught are again only functions of temperature. Okay, and we know T1 and T2, so we get them directly. Here P2 is not equal to P1. There is minor differences, so we need to actually solve for it, right? We can't just write down as zero. So we need to actually plug in the numbers. So once you plug in the numbers, this is the mass flow rate. This is H2 and H1, as we already found out before. This is the value of T naught given in the question. S naught 2, S naught 1, which we got from table 822. Okay. And then R, the gas constant for air. Well, it's the universal gas constant divided by the mass, molar mass of air. This molar mass is again given in table 1. Ln P2 by P1. So here, you don't have to do any conversion, right? It's just a ratio that you're looking at. So we can just divide 9.7 by 10, which is the P2 and P1 here, right? And when you sum it up, when you calculate it, it comes out somewhere around 14,103 kilojoule per second, or you could say 14.1 megawatt. Okay, so this is the change in flow exergy of airstream, right? This is the exergy increase of the flow stream. Okay, now we also need to calculate the exergy change of the hot combustion gases. All right, and in energy aspect, because energy is conserved, we know that the energy lost by the hot combustion gases is equal to the energy gained by the cold uh, gases here, right? Which is the cold air, so or the cold stream in the heat exchanger. Now, before we even go ahead and solve for the exergy rate for hot combustion gases, right? What is the exergy difference? Anyone wants to guess whether it's going to be equal to 14.1? Is it going to be higher than this or lower than this? What do you think about the exergy change for the hot combustion gases?
It will be higher.
Okay, and why do you think it'll be higher?
No, I think it will be lower because the pressure is lower.
Uh, no, the pressure doesn't have much to do with the flow exergy. I mean, it's essentially dictated by temperature. So, I mean, I'm not talking about the specific flow exergies. I'm talking about like the change in exergy, right? So you see, it's coming out at a higher temperature, and there is some change in exergy for the hot stream, right? And therefore you have the exergy being transferred from the hot stream to the cold stream. All right. So I would take Abdul Malik as saying that it's going to be higher. What about others? What do others think? Is it going to be higher? Is it going to be lower?
Doctor, I didn't understand.
Okay. So what I'm trying to ask here is, we calculated the net change in flow exergy for the airstream, right? We calculated m dot ef2 minus ef1. Now we need to calculate m dot ef3 minus ef4. Okay, what is the net change in flow exergy for the hot gases or the hot stream of the heat exchanger right here. So before we go ahead and calculate, I just wanted to know what your expectation is about this value. Would you expect it to be greater than 14.1, which is the change for air, or would you expect it to be lower than this value? Uh, okay, no worries if you are still not so clear. This is why we have the Exergy balance equation to help us with it. Let's just go ahead and calculate, and then we'll see when we put everything together. Thank you, Abdul Malik, for answering. Your answer is correct. We'll see how. Okay, so when you calculate the change in exergy for the hot combustion gases, again, is the same formula you need to plug in. We're treating the combustion gases as hot. We are assuming it to be air. So you just have to use the ideal gas table and plug in the numbers. These are the specific numbers that come up, right? And when you calculate it, um, it comes out to be 16.93. Okay, so of course, when we take EF4 minus EF3, you know, it's going to be minus because the exergy at state 4 is lower than the exergy at state 3. But when you look at the net change, what is the difference, right? So the difference between these two, between the exergy flow exergy rate for the hot stream, right? This difference here is higher than the difference that we have for the airstream. So basically what I'm trying to tell you is the exergy lost by the hot stream is more than the exergy gained by the cold stream. Okay. And so there is some exergy being lost somewhere, right? And that is what part C is. It's about calculating the exergy destruction. Okay. So again, when we plug in this equation right here, we know there's no heat transfer external to this heat exchanger, and then the heat exchanger there's no work done. So all you have is these two streams. Okay, so whatever is the exergy change of the hot stream would be equal to the exergy change of the cold stream or air plus some amount of exergy destruction. Okay, so when you put in these numbers here, plug in the differences that we just calculated, it comes out to be 2.83. All right, so exergy increase of the compressed air, which was which is the desired output for a heat exchanger here, is 14.1. Okay, so sorry. So this exergy increase of the compressed air happened at some cost, right? We lost the exergy from the hot combustion gases, but the amount of exergy that was lost from the combustion gases was 16.93 megawatt, a little bit higher than what the air uh, eventually got. And the difference between this exergy changes is where the exergy got destroyed, right? And this comes out to be 2.83. So this is a very clear example and a good example to show you that although energy gained by compressed air is exactly equal to the energy lost by combustion gases, which is what we used to calculate the temperature of the exit gases, but exergy is not this exergy does not exergy gained by compressed air is absolutely not equal to the exergy lost by the combustion gases, right? And that's simply because energy is conserved, exergy is not, because exergy can be destroyed. And depending on how much exergy is destroyed, well, the exergy increase of compressed air would be different.